Greetings and welcome to Lecture 7.2. We're going to start discussing the elimination method of solving systems of linear equations. So in last lecture, we dealt with graphing to find the solution, but graphing isn't always the easiest thing to do. It's fine if we have whole numbers, but when we're dealing with decimals or fractions, it becomes more complex. So let's figure out another way of solving a system of equations without having to go through the hassle of graphing. Graphing has its great moments, but it does have its limitations. So this method we're going to discuss is called the elimination method. There's a little bit of groundwork I want to set up, and that is if we let A, B, C, and D represent algebraic expressions. If A equals B and C equals D, then if I add A and C, that will equal B plus D. Now think about it. Let's say A is, we'll just simplify it. We'll say A is 2 and B is 2 and C is 3 and D is 3. Well, 2 equals 2 and 3 equals 3. If I add them together, 2 plus 3 is going to equal 2 plus 3. So 5 equals 5. So I don't change anything. It's like a different number, but I don't change the equality of it. So let's take an example and use what we have now at our disposal to solve the system x plus y equals 4 and x minus y equals 2. There's a couple ways of looking at this. I'm just going to do it to where I'm going to consider that A equals x plus y and B equals 4, C equals x plus y, and D equals 2. And using what I know about the A plus C equals B plus D, I'm going to add the two of them together. So x plus y plus x minus y will equal 4 plus 2. But that gives me x plus x gives me 2x. Y minus y eliminates the y. So I have 2x equals 6. And now I can just solve for x by dividing both sides by 2. So x will equal 3. I still don't know what y equals, but that's okay. I can backfill using what I know about x, go back to one of my original equations, plug it in, and solve for y. So x plus y equals 4. When x is 3, y will equal 1. So my solution to this system is 3, 1. And I can double check that it does satisfy. When x is 3, y is 1. X plus y equals 4. 3 plus 1 equals 4. 4 does equal 4. X minus y equals 2. 3 minus 1, does that equal 2? 2 equals 2. So 3, 1 satisfies both the equations of the solution, and therefore it's a solution to the system. I know that was a mouthful, but it is the whole entire, not only does it satisfy both equations, it satisfies the system. If you want to see visual evidence, here's the graph of it. So I have x minus y equals 2, x plus y equals 4, and they cross right at 3, 1. That is the point of intersection. It's not always bad to see that it's the visual evidence to support the math part of it, but it's not always necessary. Let's use our elimination method again to solve another system of equations. X plus 2y equals 4 and x minus y equals negative 5. Now if I add these both together, I'm going to get 2x plus y equals negative 1. That doesn't eliminate a variable, but I have at my disposal the multiplication property of equality. If you remember that, it means if I multiply one side of an equation by a number and I multiply the other side by that same number, then nothing really changes. So at least my solution won't change. It will look a little different, but it won't change. So I'm going to take this second equation and multiply it by negative 1. Now you may ask me why I did that. Because ultimately I want to add the two of them together, and I already have a positive 1. I just need a negative 1 to be able to cancel out or eliminate my x's. So I'm going to multiply every term by -1. -1 times x is -x. -1 times -y is +y. -1 times -5 is +5. Now my new system is x plus 2y equals 4 and -x plus y equals 5. Now I'm going to combine them by adding them. X minus x is 0, 2y plus y is 3y, and 4 plus 5 is 9. Now I have a simple equation of 3y equals 9. And I can solve for y equals 3. But I'm not done. I still have to go back and solve for x. So plugging it into one of my equations, doesn't matter which original equation you plug it in, you can plug it into either one. I'll just take the first one. X plus 2 times 3, our found value of y, equals 4. So x plus 6 equals 4, therefore x equals -2. So my solution set is -2, 3. And again, here is the visual evidence of that. I've plotted my two lines and they cross at -2, 3. Let's try another example. So we have the system of 2x minus y equals 6, x plus 3y equals 3. I can't eliminate my variables here, but I'm going to choose to try and eliminate the y because I have a negative y and I have a positive 3. So if I multiply that top equation by 3, I'll get a negative 3y and a positive 3y, and I'll ultimately be able to eliminate the y. I could try to eliminate the x's, but I'm going to just choose to eliminate the y's right now. So I'm going to multiply 3 to 2x, get a 6x. 3 to -y gets in the -3y, and 3 to 6 gets me 18. So my new equation is 6x minus 3x equals 18, and then I'm going to combine it with x plus 3y equals 3. That gives me 0 y's, which is the whole point. I need to eliminate at least one of the variables. 7x equals 21. I can solve for x, and x equals 3. Still need to find the numerical value of y, so I'm going to plug it into one of my equations. I'll just choose the top one just because it's simple. 2 times 3 minus y equals 6. 6 minus y equals 6. Y equals 0. So my solution set is 3, 0. Now in the previous example, we've only had to manipulate one of our equations to be able to get one of our variables to be eliminated. Occasionally that's not the thing. Sometimes we have to manipulate both of them, both equations, to be able to eliminate one of the variables. So here's the secret. You just decide which variable you want to eliminate. It doesn't matter if you eliminate the x's, it doesn't matter if you eliminate the y's. You decide. You have to have one of the eliminated variables to be negative and one of them to be positive. For me, I chose my top equation to be, I'm going to eliminate my x's, and I've chosen the top one to be positive and the bottom one to be negative. It doesn't matter. I could have chosen the top one to be negative and the bottom to be positive. As long as they're opposite signs, I can eliminate them after going through and multiplying. Alright, so the top I need to multiply by 3, and the bottom equation I need to multiply by -2. So I'm going to multiply that all the way across. That gives me the two new systems of 3 times 2x is 6x, 3 times 3y is 9y, 3 times -1 is -3. -2 times 3x is -6x, -2 times 5y is -10y, and -2 times -2 is a +4. Now I'm going to add the two equations together. 6 minus 6x is 0x. 9y minus 10y is a -y. -3 plus 4 is a +1. I'm going to divide each side by -1. So y will be -1. Still going to need to plug in to find the solution for x. Again, choose any of the original equations. You don't want to choose one that you've manipulated. Just go ahead and choose one of the original ones. 2x plus 3 times negative 1 equals negative 1. 2x minus 3 equals negative 1. Add 3 to both sides. 2x equals 2. And x equals 1. So my solution is 1 comma negative 1. Do remember that the x always comes first and the y is second. It is an ordered pair. Okay, here's your class problem. What I would like you to do is solve this system of equation by elimination method. 3x plus 5y equals negative 7 and 5x plus 4y equals 10. Now I don't care which value that you eliminate, but just follow the steps to solve the problem by elimination. So I want you to have that ready to turn in for the next class session. Let's try a little bit more complex problem. I know you love fractions, so let's try the system 1/2 x minus 1/3 y equals 2 and 1/4 x plus 2/3 y equals 6. Now, I could multiply the top by a 2 and that would get me a negative 2/3 y, and then I have a positive 2/3 y. But instead of doing that, why don't we just eliminate the fractions? I know y'all don't like them, so let's multiply the top equation by its LCD, which is 2 times 3. So I'm going to multiply each term by 6. And then we'll eliminate the fractions for the second equation by multiplying it by its LCD, which is 4 times 3, which is 12. Once we do that, we will eliminate our fractions. So my new system is going to be 3x plus 2y equals 12, 3x plus 8y equals 72. Now the only thing I have to do here to be able to eliminate the x's is to multiply one of these equations by negative 1. I'm just going to choose the top one. Okay. So negative 1 times 3, negative 1 times negative 2y, and negative 1 times 12 will get me my new system of negative 3x plus 2y equals negative 12, 3x plus 8y equals 72. We're going to combine this new system with the result of 0x plus 10y equals 60. We can solve for y, and y will equal 6. Plugging 6 back into one of the original equations, the original ones, not the one that we manipulated, one of our original ones, we'll have 1/2 x plus 1/3 times 6 equals 2. 1/3 times 6 is a 2, so now I have negative 1/2 x minus 2 equals 2. Add 2 to both sides. I have 1/2 x equals 4. Multiply by its reciprocal, which is 2, so multiply by 2, and x equals 8. Therefore, my solution set to the system is 8, 6. Now there are two very special systems that will probably sometimes give you trouble. Now graphically we were able to graph two parallel lines and see that they never cross, and therefore we had an empty set solution. But let's do this mathematically. I'm going to use my elimination method. So I have 2x minus y equals 2, 4x minus 2y equals 12. If I multiply the top equation by negative 2, I get negative 4x plus 2y equals negative 4. If I combine the two, I have 0x plus 0y equals 8, and therefore 0 equals 8. No, it's a false statement, so right then and there I should know that these are parallel lines. The second very special one is where when you work through the problem, you get something that looks like 0 equals 0. That's always true. That means the lines sit on one another. They are the same. So that's it for this lecture. Until next time, be seeing you.